Imagine this scene. A secret agent walks toward a locked door. He opens his eye. A red laser scans across it. The machine beeps. And the door opens. Very cool, very cinematic, and also very Hollywood. Because in real life, iris recognition does not need a dramatic red laser that looks like it is about to toast your retina. What actually opens the door is mathematics, not magic, not Agent 007. Mathematics, geometry, signal processing, binary codes, and probability. In one large deployment in the United Arab Emirates, billions of iris comparisons can be performed every day. And in large-scale analysis, researchers have studied around 200 billion comparisons between different iris patterns. 200 billion. That is the kind of number that makes a spreadsheet open once and immediately reconsider its career. But here's the real question. How can a tiny region inside your eye become a key to your identity? Today, we are going to open up the iris recognition pipeline, from a real eye image to a binary code, and from that binary code to a decision. Same person, or not. So the whole algorithm can be seen as one long translation. First, biology becomes geometry. Then geometry becomes a signal. Then the signal becomes bits. And finally, the bits become probability. That is the path we are going to follow. So why use the iris in the first place? Why not a face, a password, or a fingerprint? First, look at the eye. At the center, we have the pupil, the dark opening that expands and contracts to control incoming light. Around it is the iris, the colored ring between the pupil and the white part of the eye. From far away, the iris may look simple, nothing too dramatic, but if we zoom in, it becomes a tiny biological landscape. There are folds, ridges, crypts, fine streaks, tiny structures that look as if nature gave a mathematician a paintbrush and then told them to improvise. The important part is this. These patterns are highly distinctive. Even identical twins do not have identical irises. Even your left eye and your right eye are different patterns, so faces may look similar, names may repeat, passwords may be forgotten. But the iris has a naturally random structure that is extremely hard to imitate. That is why it is such a powerful biometric trait. Now the computer has a problem. How do we turn this complex biological texture into something we can compare mathematically? If biology is going to become geometry, the first question is, where exactly is the iris? The step sounds simple. Find the iris in the image. But simple is just the trap at the beginning. The computer must locate the inner boundary of the iris, where it meets the pupil. It must locate the outer boundary, where the iris meets the white part of the eye. It must detect eyelids, it must ignore reflections, and it must deal with eyelashes, which are basically tiny black intruders with excellent timing. The naive approach is tempting. Draw two circles. One around the pupil, one around the iris. Done. Unfortunately, real eyes did not sign a contract with high school geometry. The pupil is often not a perfect circle. The two boundaries are not always concentric. The outer iris boundary may be partly hidden by eyelids. And if we force everything into two perfect circles, we may extract the wrong data. So the algorithm needs something more flexible. This is where active contours appear. Imagine dropping a soft elastic loop onto the eye image. The loop is not fixed, it slides, it stretches, it contracts, it follows places where the image changes sharply. In plain English, it tries to cling to the real boundary. But the loop cannot wiggle randomly. It must stay smooth, it must close on itself, and it must be able to continue through parts that are hidden or interrupted. To do this, Dogman models the iris boundaries using discrete Fourier series. On screen, the idea is simpler than the symbols. Boundary samples become Fourier coefficients. Those coefficients behave like rotating vectors, and the rotating vectors reconstruct a smooth contour. This is just Fourier giving a flexible boundary a mathematical language. So instead of saying, the iris is just two circles, the algorithm says, let the boundary bend with the data, but keep it smooth enough to trust. That is the first major step. Find the correct region. Because if we crop the wrong part of the eye, then every beautiful equation after that is just being beautifully wrong. After finding the iris, we face a new problem. How do you compare a ring-shaped texture across two different photos? The iris is a ring. But computers love organized data, so the computer looks at this circular structure and quietly asks, can I turn you into a rectangle? And the answer is yes. We slice the iris by angle. Then we unwrap it into a flat strip. like cutting open a rubber ring and stretching it into a rectangular carpet. Instead of asking where a pixel is on the original image, we ask two simpler questions. R, the position from the pupil boundary to the outer iris boundary, and theta, the angle around the eye. On screen, this gets a compact name. I of xy becomes I of r theta. The result is that a curved iris region becomes a normalized rectangular strip. This matters a lot, because your pupil does not stay the same size. In bright light, it contracts. In darkness, it expands. But the algorithm does not want every change in pupil size to completely distort the iris pattern. By mapping the iris into a normalized coordinate system, different images of the same iris become easier to compare. But there is another very human problem. People do not always look straight into the camera. Sometimes the eye is off axis. When that happens, circles may appear as ellipses. So the visual idea is, a circle in 3 dimensions becomes an ellipse in the image. A few coefficients from that ellipse give a short estimate of the gaze angle. The formula only needs to appear briefly. It is a bonus detail, not the main pipeline. Then, an affine transformation makes the eye appear closer to a frontal view. In other words, the algorithm sees your side eye and says, "Do not worry, I will correct that." Then comes the final villain of this stage: eyelashes. Eyelashes may look great in a portrait, but in iris recognition, they are noise. If eyelashes cover the iris and we encode them, the iris code would contain information from the eyelashes, not from the iris. So the algorithm uses statistics. It examines the intensity histogram of the iris region. If there is an unusual dark cluster of pixels, that may indicate eyelashes or occlusion. Those pixels are added to a mask. A mask simply says, "This region is suspicious. Do not trust it." So after this step, we have 3 things: a correctly segmented iris, a normalized iris strip, and a mask that tells us which regions should be ignored. Now we are ready to turn the eye into code. At this point, we have a clean iris strip. But here is the problem. On the screen, we have an iris strip. To a human, it still looks like a complicated texture. But for a computer, a strip of texture is still too much information. It has brightness, noise, tiny local patterns, small distortions. So the algorithm needs to ask a more stable question. Not, what is the exact brightness here, but what is the local pattern doing here? The tool used for that question is the Gabor wavelet. Think of a Gabor wavelet as a tiny wave pattern. It oscillates, but only inside a local window. Like a small magnifying glass, that asks one question: what kind of local pattern is happening here? The Gabor filter scans across the iris strip. At each location, it produces a response. But the algorithm does not need to keep the whole image. It mainly cares about phase information. Phase tells us the state of the local wave response. Which direction is the pattern leaning? Which region of the phase plane does it fall into? And from that phase information, the algorithm quantizes the answer into bits. Not a long paragraph, not a heavy image file, just zeros and ones. Gradually, the whole iris strip becomes a long binary sequence. This sequence is called an iris code. A biological pattern full of folds, streaks, and texture has now become a string of bits. Now biology has become geometry, and geometry has become code. So what do we do with 2 codes? One comes from the probe eye image, the other comes from the database. But before we count disagreements, there is one very practical detail. The eye may be slightly rotated when captured. So even if 2 iris codes came from the same iris, their bits may be shifted around the circle. At shift 0, the disagreement can look too high. So the matcher tries a small set of circular shifts. The best alignment is the one that makes the disagreement count smallest. Here, a small shift drops the score from about 0.44 to about 0.17. The identity did not change, the alignment did. But not every bit deserves a vote. Some parts may be covered by eyelids, some parts may be covered by eyelashes. Some parts may be corrupted by reflection or noise. So we apply the mask. Only bits that are valid in both images are counted. Now we use XOR. If 2 valid bits are the same, OR gives 0. If they are different, XOR gives 1. Finally, the full formula appears. It says the same thing the animation just showed. XOR, the 2 codes, keep only the bits allowed by both masks. Then divide the number of valid disagreements by the total number of valid bits. This is the Hamming distance. If the score is below the threshold, the system accepts the match. For the same eye, one shift can suddenly make the codes line up. For a different eye, no shift really saves it. the disagreement stays close to chance. And that is the bridge to probability. Now this may feel almost too simple. We reduced an eye to bits. Then we counted disagreements. So why should anyone trust this? The answer is not in the eye anymore. It is in probability. Why should counting bits be reliable? Imagine comparing two irises from two different people. If their iris codes are truly independent, then each bit comparison is like a coin toss. Same or different, heads or tails, almost random. So when we compare many bits, the fraction of disagreement should concentrate around 50%. In other words, different eyes tend to have a Hamming distance near 0.5. This is where the binomial distribution enters. When you toss many coins, the results do not scatter randomly everywhere. They gather around the expected value. The same intuition applies here. But biology is not a perfect casino. Nearby iris structures are related, and Gabor filters can make nearby bits correlated. So the raw number of bits is not the same as the number of independent trials. The effective number of independent comparisons is smaller. That makes the real different eye curve wider than the ideal independent bit curve. In large-scale iris comparisons, different eye comparisons form a distribution centered near 0.5, and the tails of that distribution drop very quickly, extremely quickly. That means the chance that two different irises randomly produce unusually similar iris codes is very small, not because the system feels they look different, but because probability says, this similarity is far too unlikely to be random. That is the genius of the method. Iris recognition is not just image matching, it is a statistical test of independence. If two codes behave like random coin tosses, we say, different irises. If they agree much more than randomness would allow, we say, likely the same iris. And that is how a string of bits becomes an identity decision. No drama, no red laser. Just XOR, Hamming distance, and a probability distribution quietly doing its job. So the full story is one long translation. We start with an eye image. We locate the iris, we unwrap it into a normalized strip, we ignore regions corrupted by eyelids, eyelashes, or reflections. We use Gabor wavelets to encode texture into an iris code. Then we use XOR and Hamming distance to compare codes. Finally, probability tells us whether the similarity is random or meaningful. Biology became geometry, geometry became code, code became probability. Iris recognition is not magic, it is biology meeting mathematics. Today, iris systems are also moving beyond the old stop and stare interface, toward recognition while people are moving, looking off axis, or standing farther away. From stop and stare to iris on the move. The window to your soul, with enough mathematics, becomes a key to your identity, and probability becomes identity. And next time you see a security camera, do not worry. It probably does not know what you are thinking, but with a good enough iris image, it may know whether that eye is yours. Thank you for watching.